Okay, let's try and unpack this. So imagine you're working at a food company, right?
Uh-huh.
Making these huge batches of, say, cereal or maybe some fortified drink.
Yeah, massive quantities.
Exactly. And you've got to guarantee, absolutely guarantee, that every single serving meets the nutritional label claim.
Right, consistency is key.
But the thing is, ingredients, even added nutrients, they don't always mix perfectly evenly through that whole massive vat.
That's a real manufacturing headache. You can get hot spots or areas with lower concentration.
So how do you figure out the total amount of, like, a specific vitamin in the entire batch if its concentration might be higher here and lower over there?
That is a really interesting problem. Ensuring that consistency and making sure the label's accurate across these huge volumes, it definitely needs a precise method, not just a simple average.
Absolutely. And that brings us right to our source for today. It's titled Nutrient Integration, a Differentiated Approach.
Sounds pretty mathematical.
It does, yeah. Sounds like something straight out of calc class. But our mission here, based on this source, is to see how these, abstract math ideas actually show up in something really tangible, like the food you eat every day.
Right, connecting the theory to the real world.
Exactly. So this deep dive is really for you, whether you're maybe neck deep in calculus homework right now, or maybe you're just curious how stuff works behind the scenes.
And the core idea, the main application the source highlights is using integration, that calculus concept in food science,
To do what specifically?
to calculate the total nutrient content in a production batch.
Okay, integration. Now, if you've taken calculus, you probably think of it as like finding the area under a curve, or maybe accumulating something over time.
That's the usual starting point, yeah. Accumulation is the key word there.
But how does finding the area under a curve connect to vitamins in a giant tank of juice or a mixer full of cereal?
Ah, that's the critical link. See, if the nutrient was perfectly, absolutely uniformly mixed.
Which it isn't always.
Right. If it were perfectly uniform, you could just measure the concentration in one spot, multiply by the total volume or weight, and boom, you're done.
Simple multiplication.
But like you said, that ideal situation, it's often not the reality. Different ingredients, densities, mixing times, things settle. You end up with variations. A bit more nutrient here, a bit less there.
So just taking one sample, getting an average, and multiplying.
Mm-hmm.
That won't give you the true, accurate total amount.
Precisely. It might be close, but it might not be accurate enough for labeling or quality control. You need something more robust.
Okay.
You need a tool that can handle that variation, and that's integration. It lets you essentially sum up the concentration across the entire volume, piece by tiny piece.
So you're adding up little bits.
Think of it like adding up the amount of nutrient in countless infinitesimally small sections of the batch. By integrating this change in concentration function over the whole volume, you accumulate the actual total amount, even if it's not evenly spread. Ah, okay, I think I get it. So integration is like the mathematical tool to find the total stuff when the stuff per unit volume isn't constant everywhere.
Exactly right. It's specifically designed for that kind of accumulation over a continuous space, like the volume of a tank or a mixer.
Okay, that makes sense for the integration part. But here's something that jumped out at me from the source title. Nutrient integration, a differentiated approach.
Good point.
Why bring differentiation into it? If the main goal we're talking about is using integration to find the total.
That's a really sharp question. It suggests there's maybe another layer to it. While integration gives you the final total,
Yeah,
understanding how the concentration is distributed, or maybe the rate at which it changes from one point to another within that batch, that might involve differentiation.
oh, okay. Like using differentiation to model the unevenness.
Potentially, yes.
Mm-hmm.
You might use principles related to rates of change, which is differentiation, to build a model of how the concentration varies, maybe based on fluid dynamics during mixing or settling rates. And that model, the one describing the variation,
That model then gives you the specific concentration function that you need to integrate to find the accurate total.
interesting. So the differentiated approach part might not be about the final calculation itself, but about the steps needed to understand the variation before you can even do the integration accurately.
That seems like a very plausible reading. Yeah. You need to understand the non-uniformity first, perhaps using methods linked to differentiation to set up the correct integral. It's about getting the inputs right for the integration step.
And the source implies this isn't just, theoretical math fun.
No, according to the source, this kind of approach is actually applied. used in food science for serious quality control, making sure those nutrition facts on the packaging are reliable.
Right, so distilling it down, the key takeaway from our source seems to be integration is more than just textbook math. It's a practical tool in food science,
A powerful one, yeah.
used to calculate the total nutrients in a batch, especially because it handles that uneven distribution. And that differentiated approach bit in the title, it likely points to how understanding the variability itself, maybe using concepts related to differentiation, is also crucial to the whole process.
Absolutely. It really reinforces the idea that the math you might be learning, may be struggling with right now,
Yeah.
it has these direct practical uses. In this case, in food manufacturing, helping make sure what we eat is accurately described and consistently produced on a huge scale.
It's pretty cool to see that connection. So this deep dive focused on nutrient content, just one specific example from our source.
Hmm.
But it makes you wonder, doesn't it? Where else might calculus be working silently behind the scenes in our everyday lives? Think about other processes involving accumulation or rates of change, especially where things aren't perfectly uniform.
Good question.
What other things that seem simple on the surface might actually rely on summing up tiny, variable parts? This food science example is just scratching the surface. Where else could you look?